In this video, we're going to graph polynomials. Before we start graphing polynomials, we are going to review finding zeros, review polynomial interaction with the x-axis, then we're going to graph a polynomial and find zeros of a polynomial. So let's go to reviewing of finding zeros. So when we find zeros, we're going to factor the polynomial completely, and we are going to do this in multiple ways because we are mathematicians, and so we're always asking ourselves, how can I do this best or most efficiently? First we're going to factor out monomials. That's always your first step. Can I get a monomial out of there? If we can, great. If we can't, that's fine. If it is a trinomial you're dealing with, you can factor it into two binomials. But if it's not a trinomial, then we're going to have to work with it in a different way. We can check on special factor patterns. Remember, that's difference of squares, sum and difference of cubes. Is it one of those? If that doesn't work, we can try factoring by grouping, which is always lots of fun. And if factoring by grouping doesn't work, then of course synthetic division, which is my personal favorite. And I know that that's true for a lot of you. If synthetic division has failed, if you have a quadratic and you have tried factoring it into trinomials, you can always try the quadratic formula. Remember that you can only use that with quadratics, but you can certainly look for irrational roots with the quadratic formula because those are still zeros. As long as they're real solutions, they're still zeros. So remember that all of those methods are valid methods to factoring a polynomial, and that in order to find zeros, we do have to have a factored polynomial. We do actually have to have equations that we can solve. Once you have factored your polynomial completely, you are going to set each factor equal to 0 and solve for x. And those should be fairly simple, short equations. Now, remember that polynomials interact with the x-axis in three ways. If you have a linear factor, for example, x plus 5, or x minus 1, or 2x plus 3, when you set those factors equal to 0 and solve for x, you're going to get one solution, and that indicates that at that factor, your graph will cross straight through the x-axis. It won't curve at all, it's just going to go straight through. Now, if your factor has an even exponent, like x plus 4 squared, or x minus 7 to the 4th, or x plus 1 to the 6th, then your factor is going to create a zero that bounces. So your graph will touch the x-axis, but instead of crossing through the x-axis, it will bounce off the x-axis. And the reason for that is that graph behaves like your factor if you zoom right in. So what does a quadratic with an x squared do? It curves. It has a U shape. X to the 4th and x to the 6th graphs also have U shapes. So if we zoom in at that 0, it's going to behave like the parent function for that factor. So an x squared or x to the 4th or x to the 6th. It's a bounce. Now, this is really important that we remember that this only works with even exponents on the factor. Notice that all of my exponents are on the outside of my factor. They are not in the parentheses. They are on the entire parentheses, quantity x plus 4 squared. If you had a factor like x squared plus 5, that is not a factor with an even exponent. That's an x squared with an even exponent. So this is not a place where the bounce, cross, or wiggle rule applies. You can set this factor equal to 0, the x squared plus 5, and solve for x. But you cannot say it bounces because that too is in the wrong place. It should be on the outside of the parentheses if we're going to classify it as a cross, a bounce, or a wiggle. The last type of behavior that we might see with factors is a wiggle through the x-axis, and that happens when you have odd exponents. So for example, x minus 1 cubed, or x plus 2 to the 5th, or x minus 54 to the 7th. which I know everybody wants to graph. Now, these exponents are all odd, and so what happens when you have an entire factor on the factor, right, outside the parentheses, is that your graph will wiggle through the x-axis. So it crosses the x-axis, but instead of going straight through, like our linear factors, it comes up and does a little wiggle. And again, the reason for that is that when you zoom into that x-intercept, your graph is behaving like the parent function for the factor. So a cubic function has a wiggle in it, as does a fifth and seventh root. And just to be absolutely sure that we do not get this confused, remember that, for example, x cubed minus 4, that is not a factor with an odd exponent. It's not, because the cubed is on the x, not on the entire factor. It would have to be outside the parentheses in order for these rules to apply. All right, we're going to graph this polynomial f of x, and in order to graph it, we need the zeros, which we are fortunate to have because this polynomial is factored for us, but we also need to know the degree and the leading coefficient so we can figure out the general shape of the polynomial. So when we get to the zeros, it's fairly easy to do because we don't have to factor anything, but first we need to establish degree. When you have a polynomial that is factored, the way you establish degree is you add up the degrees of each factor. So this first factor right here, x minus 4, that's a linear factor. It has a degree of 1. And we know that because the x has a degree of 1 and the parentheses has a degree of 1. If we look at our second factor, taken alone, that's a quadratic. It's a quadratic factor. And this quadratic has a degree of 2. We do look at the parentheses and notice that our parentheses has a power of 1 on it, so we don't need to take that into account. But if there had been a 2 or 3 on the outside of the parentheses, we would have to take that under account when we're determining the degree of the factor. So first factor, degree of 1, second factor, degree of 2. Degree of the polynomial is the sum of those numbers. So it's 3. And what that tells us is we have an odd polynomial. And so that tells us the shape. Either this polynomial starts at the bottom left and moves to the top right, or it starts at the top left and moves to the bottom right. It's one of those two. And to figure out which one it is, we have to talk about the leading coefficient. Now, usually we just look to the first term for the leading coefficient, but this is a factored polynomial, so I can't just look at the first term of the polynomial. What I can do is I can look at the front of the polynomial between the equal sign and the first set of parentheses, because if this polynomial is going to have a negative leading coefficient, there would be a negative sign right there in front of the first set of parentheses. There isn't one. And that lack of a negative sign means that the leading coefficient to this polynomial is positive. We don't really need to know its numeric value. We just need to know, is it positive or negative? So we've accomplished that. A positive leading coefficient tells me that we are looking at a graph that starts in the bottom left and moves to the top right. So that is the general shape of this polynomial. Now that we have our degree and our leading coefficients, let's just take a little moment to review end behavior, because it's always good to review end behavior. And remember that end behavior always starts the same way. We say, as x approaches negative infinity, f of x approaches something. And as x approaches positive infinity, f of x approaches something. And we just fill in those blanks. So when we're looking at our graph, I see that as my x values move left, which is approaching negative infinity, my y values are going down. This graph is moving left, but it's also moving down. And so my end behavior as x approaches negative infinity, f of x approaches negative infinity. And then as we trace the graph right, as my x values get bigger, my y values are going up as well. And so as x approaches positive infinity, f of x approaches positive infinity. And I know that a lack of a plus sign indicates that it's positive,
But remember that it's important to put those plus signs just to sort of differentiate between positive and negative infinity, and also so that you don't forget to put the negative on the negative infinity, because those are two different spaces. So you really, really need to put your plus signs on your infinities. All right, guys, let's talk about zeros. Remember that we find zeros by setting our factors equal to 0 and solving for x. So my factors here are x minus 4, and then 2x squared minus 2x plus 1. X minus 4 solves to x equals 4, and we know from our review of interactions with the x-axis that this is a linear factor. It has an exponent of 1, which means that we just cross the x-axis at x equals 4. There's no wiggle going on there, which is interesting because this is a cubic function and it should wiggle somewhere, right? Now let's look at the 2x squared minus 2x plus 1. We could use the quadratic formula to solve this. I'm looking at it and I notice that it's not really factorable. But before I embark on the quadratic formula, I was given a function with a factored polynomial. My question is, why isn't the 2x squared minus 2x plus 1 factored? Does it have solutions? And so let's look at this and let's ask ourselves, well, could there be imaginary solutions to this quadratic? And we actually have a method that we can use to determine whether the solutions to the quadratic are real or imaginary. And that method is called the discriminant, which I know you guys have just been waiting to use again. And remember that that's b squared minus 4ac. And so the discriminant for this quadratic is negative 2 squared minus 4 times 2 times 1. And that is 4 minus 8, which is negative 4. And a negative discriminant means you have two imaginary solutions. And so we don't need to solve that quadratic because the imaginary solutions are not solutions that we can put on our graph. That f of x is not crossing the x-axis at those solutions. It crosses the x-axis at 4. It does not interact with the x-axis again. So we can just leave the 2x squared minus 2x plus 1. We don't have to solve anything there. Now, if we're going to make a nice and accurate graph of this function, we probably need some values. And so we're going to make a table of values. And I'm going to put the 4 here. We like that 4 because we know the y value at 4 is 0. And then what we're going to do is we're going to look at one point on either side of the 4 and try to determine which direction we might need to go. We might need to go in both directions, but we might only need to go in one. So I'm going to look at 5 first. I'm going to plug 5 into f of x. So 5 minus 4 times 2 times 5 squared minus 2 times 5 plus 1. And when you do that, you get 1 in the first parenthesis. And then 2 times 5 squared is 50 minus 10 plus 1. So 1 times 41, which is 41. That is a big number. That's a big number. And if I plug in 6, we're just going to get even bigger because what's happening is that we are squaring those numbers and multiplying by 2. And so, 2 times 6 squared is 72. And so that's just even bigger. So what we're going to do is we're going to look in the other direction and see if those numbers are more manageable, things that we can actually graph. So if I plug in 3, I get 3 minus 4, and then 2 times 3 squared minus 2 times 3 plus 1. And that is negative 1 times, so 2 times 3 squared is 2 times 9, which is 18, minus 6. So it's 12 plus 1 is 13. So it's negative 1 times 13, which is negative 13. That's a more manageable number. And what we're going to do is we're going to keep looking at numbers smaller than 3 and see if we can get a better picture of this graph. All right, so we're going to plug in 2. And so we get negative 2 in the first set of parentheses, and then 2 times 2 squared, that's 2 times 4, which is 8, minus 2 times 2, which is 4. So 8 minus 4 is 4, plus 1 is 5. times the negative 2 from the first parentheses is negative 10. We're going to plug in 1 now. So 2 times 1 squared minus 2 times 1 plus 1. And so this is negative 3. And then 2 times 1 squared is 2 minus 2 is 0 plus 1. So negative 3 times 1, which is negative 3. We're going to try 0. And we love plugging 0 in because it's very easy to do. Oh guys, do you see that I put a squared on that first set of parentheses? No. What was I thinking? All right, so 0 minus 4 is negative 4, and the second set of parentheses, 2 times 0 squared minus 2 times 0 plus 1, just simplifies to 1. So it's negative 4 times 1, which is negative 4. And I am going to stop here. And the reason I'm going to stop here is that what I have in my y column are negative 4, negative 3, negative 10, negative 13, and then 0 and positive 41. And what that has told me is that I have found the wiggle in my cubic graph. If we start at negative 4 and go up to negative 3, right, we're going up, and then we come back down to negative 10, go further down to negative 13, and then go back up to 0, and then up to 41. I found that wiggle in the cubic graph. And so I don't need to plug in any more numbers and find any more values. What is likely to happen after the negative 4 is that our values just get more and more negative and pretty rapidly too. So what we're going to do is we are going to actually graph those points. All right, so I have the point 0, negative 4. It's right there. I've got the point 1, negative 3, 2, negative 10, 3, negative 13, 4, 0, and then 541, which is just off the charts. And what we're going to do is we're going to connect those dots. I know I start at the bottom left and end in the top right, and the reason I know that is because I established end behavior using the degree and the leading coefficient of the polynomial. And so there's my polynomial right there. And it is not perfect, but it is pretty accurate. And we did that all without a calculator, which is, I think you all will agree, good times. All right, we are now going to find all the zeros of a given function. And so I have this function f of x right here, and we are so lucky that it is in standard form, which means that to find the zeros, we get to factor it. And that's just the best news all day, right? So remember, finding zeros, what you do is you set each factor equal to 0 and solve for x. I'm looking at this polynomial, and you may notice that it is factorable by grouping. You can factor by grouping with it. And if you want to go ahead and do that, that's totally fine. But I thought that you guys might need a little refresher on using synthetic division to factor a polynomial. And after all, who doesn't love to use synthetic division to factor a polynomial? So that's how we're going to do this polynomial. So if I'm using synthetic division to factor the polynomial, I have to find all of the possible rational roots. And to do that, what I do is I look at the factors of the constant and the factors of the leading coefficient. So I need to identify my constant, and in this case it's 12. And then I also need to identify my leading coefficient, which in this case is 1. That x cubed has a leading coefficient of 1. Now my constant being 12, I have to look at all of the factors of that number. So the factors of 12 are 1, 2, 3, 4, 6, and 12. We are lucky that our leading coefficient is 1 because that's only one number that we have to deal with. And so to find our possible solutions, what we do, that plus or minus is very important because what we're looking at is both the positive and negative, is we make ratios of all of our factors of our constant over every factor of the leading coefficient. So my ratios here are 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, and 12 over 1. And we can, again, go ahead and write those as just the list of whole numbers that they are. You do not have to show the over 1 like that, but it's important for you to remember where those numbers came from. If, for example, our leading coefficient had been 5, we would have a list twice as long because we'd have each of these numbers over 1 and then each of them over 5 as well. But my rational zeros for this are 1, 2, 3, 4, 6, and 12. And so that is a list of 12 numbers because we're looking at both positive and negative that we can try and attempt to find the zeros for this polynomial. So I'm looking at the polynomial and I see that we have a leading coefficient of 1, that we end with a 12, a positive 12, but in between we have some negative numbers. And to me that says I'm likely to have a negative solution to this problem. I'm likely to have a negative 0 because we're going to have some sign changes that happen there. And because we have the 3 and the 4 in the middle, but a 12 on the end, I'm looking at something that's bigger than 1. And so what we're going to do is we're going to try negative 2. So set this up, list my coefficients. Bring that first number down and multiply. Oops, sorry guys. Multiply 1 times negative 2 is negative 2. Negative 3 plus negative 2 is negative 5. Negative 5 times negative 2 is 10. Negative 4 plus 10 is 6. And 6 times negative 2 is negative 12. And so we have a remainder of 0, and we have found a factor. That's very exciting. It's also important to have a little try space where you can keep track of the numbers you've tried. But we found an actual 0. Look at us. And I know what you're thinking. You're thinking, Ms. Kiddush, you're a math teacher, and you've probably already worked this problem. But I promise you guys that my first guess was negative 2, and it just worked out fabulously. And again, the reason I chose negative 2 was because of the 12 at the end, the 3 and the 4 in the middle, that there's a kind of a big distance between the 3 and 4 and the 12, and because of the sign changes there. Now, we could keep going with synthetic division, which is fun, I know, but you can also write your quotient here as a polynomial. So this is x squared minus 5x plus 6, and we can find the remaining zeros by setting this equal to 0 and solving. So I can factor this. It is factorable. It's x minus 2 and x minus 3. And so I get x equals 2 and x equals 3. And so we found all of our zeros, and wasn't that fun? Now, if we had done synthetic division with a number that was not one of our zeros, let's say we tried 1 and it didn't work, what you would do is you would just cross it out and try again, right? What's the worst that can happen? You did an extra synthetic division. You had fun doing it anyways, right? All right, guys, so that's how you find zeros with synthetic division. Remember that you are welcome to use any factoring technique on these polynomials. So if you looked at this problem and said, I want to solve that by grouping, go right ahead. That is totally fine. I will caution you, though, this polynomial has zeros negative 2, positive 2, and 3. If you factor this by grouping, you're going to end up with an x squared minus 4 factor. Remember your plus or minus when you're solving x squared equations.